go ahead and move on to 9.6. 9.6, conservation of mass. Okay, conservation of mass. Conservation of mass basically says what goes in must come out. And it says, simply stated, the conservation of mass says that we cannot create or destroy a mass. Okay, you cannot create or destroy mass. That kind of falls apart a little when you start talking about quantum mechanics, when you talk about, you know, how mass can be converted into energy. You know, that's a different story altogether. Okay. Now, conservation of mass, as you can, so you cannot. So basically, what goes in must come out, or if you know, that type of thing. So let's go ahead and just jump right into the examples and see if we can just run the examples and see if it makes any sense to us. Let's look at example 9.3. Example 9.3 says, how much water, so we're on page 282. On page 282, it says, how much water is stored after 5 minutes in each of the tanks shown in figure 9.5? How long will it take to fill the tanks completely, provided that the volume of each tank is 23 meter cubed? Assume that the density of water is 1,000 kilogram per meter cubed. Okay, so the first one and the second one with both the going ins is 2 kilograms per second, right? So you are adding, in the first one, you're putting in 2 kilograms per second, and there's no out, okay? So you have going in, but nothing's coming out. It's an enclosed box. Enclosed, not a box, but a cylinder with a tank. It's a tank, okay? With a volume of 12 meter cubed. Water is 1,000 kilograms per meter cubed. Okay, blah, 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 blah. Okay, so we're gonna put in this amount, right? So this is what's going in per second, and we want to fill this much, right? So we want to be able to, so we want to find out how long it takes to add. The mass that is going in is what? The mass that's going in is 2 kilograms per second. So mass in is 2 kilograms per second. Okay, whereas if I use these, I'm gonna have to fill, when I fill this up, how much mass am I gonna fill? I'm going to get rho is equal to m divided by v. So m is going to be equal to rho v, right? So I have rho, which is 1,000 times 2, right? So I'm going to get, this is going to be 1,000 kilograms per meter cubed times 12 meter cubed, right? So the meter cubes go away. I'm going to add this many kilograms, right? This is what I'm at. So this is how much I'm going to store in here. This is the mass I'm going to store in here, right? But I'm putting this much mass in per second, right? So every second, I'm going to put in 2. So how many seconds is it going to take to fill that? I just divide it, right? So it's going to be 12,000 kilograms divided by 2 kilograms per second. Kilograms cancel out. I'm going to get 6,000 seconds. Because the seconds, if I multiply top and bottom by seconds, I end up with 6,000 seconds. Okay, so 6,000 seconds is what? If I go to minutes, I divide by 60, right? And get this many minutes, which is basically an hour and 40 minutes, I guess. Yeah, I'm right. That's right. Okay. So this is the same. So what's the difference between this guy and the next one? The next one is that I have a little hole here where now I have 1 kilogram per second leaking. Okay, so I have in and I have out. Right. So the total going in is going to be whatever's going in minus what's going out. So now the mass going in is going to be not 2, but it's going to be 1 kilograms per second. So instead of dividing this by 2 kilograms per second, I now divide this by 1, which makes this guy here 12,000 seconds. So now I'm looking at 12,000 seconds. So it's obviously going to be 200 minutes, right? 200 minutes. Okay, does that make sense? You understand the conservation of mass here? So whatever goes in, if it goes in, it comes out, right? So if you have more coming in than going out, you're going to accumulate, right? You're going to add here, right? Okay. That's 9.3. Okay, let's see if we do 9.4. Next example. Next example says, we are interested in determining the mass flow rate of fuel from gasoline tank of a small car to its fuel injection system. The gasoline consumption of the car is 15 kilometers per liter when the car is moving at a speed of 90 kilometers per hour. The specific gravity of gasoline is 0.72. If there are 1 million of these cars on the road, how many kilograms of gasoline will be burned every hour? Okay. So let's go start with the specific gravity. We have specific gravity of gasoline is 0.72, which means that it is 720, right? Because specific gravity is the gravity, specific gravity is the rho of gas divided by the rho of water, right? Which is 1,000 here, right? So the gas is going to be 720, right? 720. So this is going to be 700 kilograms per meter cubed. So this is going to be the rho of gas. Okay, because this guy here was 0.72. This guy here was 1,000, right? Okay. So we have 720, and what are we doing here? So the flow rate, okay, the volume flow rate of one car is going to be what? Volume flow rate is going to be 90 kilometers per hour, because that's the speed that we're going at. And it's going to be 15 kilometers per, what was it? Per liter. Per liter here. So basically the kilometers cancel out, and I'm going to get 6 liters per hour. This is per hour. Okay. So 6 liters per hour, right? And how many hours are we burning this? We're burning every hour. And there are how many? There are 1 million of these cars, right? 1 million of these cars, which means that we're going to burn 6 liters per hour, right? So it's going to be 6. So the mass flow rate, wait a minute. So the mass flow rate was the volume flow rate times the rho, right? So it's going to be 6 liters per hour times the rho here, which is going to be 720 kilograms per meter cubed, right? And then we have to go, I have a liter and a meter, so I have to go ahead and change this, right? These are both, they're both volumes, right? So I'm going to get 1 meter cubed is going to be 1,000 liters. So the liters cancel out. Meter cube cancel. I'm going to kind of start with kilogram per hour. I'm going to end up with kilogram per hour. And if I do all this, the book says I should get 4.32 kilograms per hour. Okay, so this is how much one car is going to consume. One car is going to use this. So if I have 1 million cars, so that'd be basically this many kilograms, right? Yep, that's it. Does that make sense? Everybody understood, followed the logic there? Okay, from here, you use a specific gravity to find the rho of gas. Using the rho of gas, we found that. And then we use the volume flow rate. We can find the mass flow rate, all right, mass flow rate, and you need this guy, which is the guy we use up here, right? We multiplied that, and then you converted the meter cubed and liters. Okay?
Question.
All right.
I have a question, Mr. On.
So we are done with 9.6.